Happy Tuesday, everyone. I hope everybody's day is going well. Welcome to the second day of our second full week of remote learning. I hope things are going well. If there is concerns about the remote learning, if you think this is getting too much, or you think there's a better way of doing something, please fill out the survey that I have at the end of today's lesson. That will kind of help me get some feedback on how things are going and what I should or need to be doing, okay? But you should have watched the Phenomena video already today, which I think is kind of cool. It shows you how sound actually involves movement, which not a lot of people think about. So that's a good thing, because remember, sound is composed of waves, which waves are a disturbance, okay? And we showed the movement of waves with the gummy bears, if you remember that video that we watched. I think that was like at the beginning of last week or the end of the week before. I forget at this point. But so keep in mind that it is movement, so that's a good idea. Today, the content we're going to be learning, where I'm going to be introducing you to sound waves specifically. So you are going to be following along with this PowerPoint and filling your PowerPoint in. Now, your PowerPoint, it can either be typed or it can be, if you print it out, you can handwrite on it, okay? If it is typed, I would just have the two screens open so you can follow along with this video and type as you go. And remember, you can always pause if I'm going too quickly, okay? So let's start in on this. Okay. So let me play. Okay. So, what is sound? So everybody knows, especially with the video, a beating drum causes the drum skin to vibrate back and forth, and a vibration is the complete back and forth motion of an object. So when you bang on the drum, the skin going down and then back up and returning to normal, that would be one vibration, okay? So, a sound wave is a longitudinal wave that is caused by vibrations and that travel through a medium. So, a longitudinal wave we talked about last week. We talked about two different types of waves, one of them being a longitudinal wave. Okay, and in a longitudinal wave, the particles of a medium vibrate in the same direction that the wave travels. So, it's parallel in that direction, same direction. As the wave passes through a medium, its particles compress together and spread out, and compress together and spread out. And that is repeated over and over again. So from that first slide, you should get that longitudinal waves are also called compression waves, and they are made of compressions and rarefactions. So remember, compressions and rarefactions are what we talked about last week with longitudinal waves. When the particles are all bunched together, that's the compression. Where they're spread apart, that's the rarefaction. So I'm going to just go along with the notes. A compression is the part of the longitudinal wave that the particles are close together, and a rarefaction is the part of the longitudinal wave where they are spread apart. Okay? So how do sound waves travel? So sound waves travel in all directions away from their source. So it's not just in one direction. Think of when you throw a pebble into the water and it goes out into like a circle. That's how sound waves travel. It goes out in all directions. They can only travel through a medium. And when I say a medium is all matter. So solids, liquid, gases, anything composed of particles, those are our mediums. So the particles in matter make up the vibrations through which the sound waves can travel. The sound waves are almost bouncing off of those particles, creating those vibrations which travel to our ear. So the particles of a medium only vibrate back and forth along the path of the sound wave. So whatever the path is taking, that's where they'll vibrate. Most sound waves travel through air, but some travel through other materials such as water, glass, and metal. Now, if you were talking to someone above the water, they'd be much more clear. Below the water, we can hear them, but it's a little more difficult. So just be aware of that when you're thinking about different mediums that sound waves travel through. In a vacuum, there are no particles to vibrate, so no sound can be made. And I'm not talking about your vacuum cleaner at home. I'm talking about a vacuum where there's no air, no matter in there. And the big example of that is space. Okay, so space is composed of a vacuum. So you cannot hear out in space because there's no particles to vibrate back and forth. Sound must travel through a medium to be detected. If there's no medium, then there will be no sound. Pitch. Pitch is something that we've all kind of heard about, but maybe don't know too much about it. Pitch is how high or low you think a sound is, and it depends on the ear sensitivity to pitches, and that can be personal, but humans in general have a range that they can hear. For instance, dogs can hear a higher pitch, though, than humans. So depending on the species of animal, the pitches change in that range, okay? So the dog whistles people talk about, they're very high pitched. Humans can't hear them, but dogs can, okay? And pitch, it has to deal with frequency and amplitude. So remember, frequency is expressed in hertz, and 1 hertz is 1 complete wavelength or cycle per second, okay? So what determines pitch? How is something high? How is something low pitched? So in a given medium, the higher the frequency of a wave, the shorter the wavelength, the higher the pitch. So remember, your frequency is how quickly those waves are coming at you. Okay, so if something has a high pitch, it has a high frequency, meaning there's a lot of waves coming at you in a short amount of time. So the wavelength must be shorter because that frequency is high. Okay, high frequency waves have shorter wavelengths and produce high pitched sounds. Low frequency waves, meaning there's not as many waves in a given amount of time, have shorter wavelengths and produce low pitch sounds. And that's because you're not getting as many of those cycles coming to you. So loudness, that's actually a scientific term, loudness. Loudness is a measure of how well a sound can be heard. So the measure of how much energy a sound wave carries is the wave's intensity, or as we talked about the past couple days, amplitude. Okay, so remember how we talked about how energy and amplitude of a wave are directly proportional? Well, the amplitude squared is proportional to the energy of a wave. This is exactly what we're talking about, okay? So the amplitude of a sound wave is the maximum distance that the particles of a wave vibrate from its rest position, okay? So the higher that amplitude, the louder that sound will be. Okay, so the greater the amplitude, the louder the sound. The smaller the amplitude, the softer the sound. So the more that those particles have to travel from that normal position, the louder the sound will be. Now, when we talk about all these words, amplitude, frequency, remember they all are part of sound. And you have a lot of common knowledge about sound, especially if you play a musical instrument. Now, a common piece of equipment for, I know at least like rock stars to have, maybe not you at home, but is an amplifier. An amplifier directly corresponds to amplitude. An amplifier can increase the loudness by receiving sound signals and increase the wave's amplitude. So that is what an amplifier is doing, is increasing the amplitude of the sound waves so that they are louder. And that's why you can hear it better. Sorry, guys. Okay, so loudness is a characteristic of a sound that can be calculated from the intensity. Remember, intensity means amplitude of that sound wave. So loudness is directly corresponded to amplitude. The most common unit to express loudness is the decibel. Okay, so decibel is used to measure loudness. And we can hear loudness over quite different ranges. So the softest sounds most humans can hear are at a level of a 0 decibel. Okay, so 0 is the bottom of the range. And then sounds that are about 120 decibels or higher can be painful to hear. So those super high pitch or they're super loud that hurts your ears, those are around 120 decibels. Rock concerts usually measure about 115 decibels, so they're right there to the almost painful part. And think of like sporting events and things of that sort that can get really loud, especially in closed arenas. That is because the decibels are so high. So like I said, amplifiers can increase loudness by receiving the sound signals and increasing the wave's amplitude. So this was the original amplitude, goes through an amplifier, this would now be the sound. So that would actually create a louder sound just going through, being fed through the amplifier. So how loud is too loud? Short exposures to sounds that are loud enough to be painful can cause hearing loss. So if you continue to listen to loud sounds that hurt your ears, it can cause you to lose your hearing. And that's because it's damaging parts of your ear. So even loud sounds that are not painful can damage your ear if exposed to them for too long. Because what happens is you have these little hairs on nerve cells in your ear, and the cochlea is a part of your ear. And those cells and those hairs, as soon as you damage them, they don't grow back. So when they don't grow back, you actually lose some of your hearing. So be careful with all those earbuds that you guys wear, okay? So using earplugs to block loud sounds, lowering volume when you're using earbuds, and moving away from a loudspeaker are all ways to protect yourself from hearing loss. Now, like I said, you can still wear earbuds, you just don't blast it so everybody else around you can hear what you're listening to. Okay? So doubling the distance between yourself and a loud sound can reduce the sound's intensity by as much as 1/4 of what it was. So again, it's decreasing the intensity, which is decreasing the amplitude. Okay, so doubling the distance, you can reduce it by 1/4 of what it was, which can help your ears in the long run. Doppler effect. We've kind of all heard of the Doppler effect, but when you think of Doppler, I think most people think of the weather radar system, not how it relates to sound. Okay, so the Doppler effect is a change in the observed frequency when the sound source, the observer, or both are moving. So when we're talking about the Doppler effect, I want you to think to yourself, if you are staying at your house, you're standing in the driveway, and think about how, if an ambulance were to drive by, how the sound changes, like how you know it's coming toward you versus going away. Okay, so this is what the Doppler effect is. When you and the source of the sound are moving closer together, the sound waves are closer together. So if that ambulance is coming towards you, the sound waves will be closer together. The sound has a higher frequency and a higher pitch, and that's because one object is moving towards the other. So the distance is no longer just the sound traveling, the ambulance is also traveling, so it makes that frequency build, okay? So you actually have, they're moving close together, so they're becoming more frequent, and if they're more frequent, that means they have a higher pitch. Okay, so the sound has a higher frequency and a higher pitch. When you and the source are moving away from each other, the waves are further apart. So now that the ambulance is driving away from you, the sound has a lower frequency and a lower pitch. And that's because the ambulance is driving away from you, so it's now spreading those distance that the frequency and the wavelengths come out. So it's a lower frequency, so it has a lower pitch. So I want you to think of this example now. So we're at a train station. This is the top one, and the train is coming towards us. So because the train is moving towards us, see these lines? These represent the wavelength. See how they're built right on top of one another. So we're going to have that higher pitch. Now, if we go to the bottom picture, the train is driving away. And because the train is taking that sound with it, it spreads out these sound waves, these wavelengths. So then we have a lower pitch. Okay. So we'll talk more a little bit about the Doppler effect because I know the Doppler effect tends to be a little tougher. Understanding why it changes as it comes and goes because it's the same sound. It's not like the ambulance driver or the train conductor is changing the sound once he passes people. It is the same sound, but they do sound different, and you know that because you can tell if the ambulance is coming towards you or driving away. Okay? So I just want to remind you, make sure you complete these notes and hand them into the assignment block for today's work. Okay? And if you have any questions, I'm always here for you.